Welcome everyone to chapter number 5. This is section 1. Here we're talking about area between curves. And in this video we're only going to deal with kind of in the x direction. We're going to be integrating with respect to x. This is kind of the classic stuff that we've been dealing with. In our next video we're going to kind of upgrade this and we're going to talk about maybe a more difficult situation about integrating maybe in the y direction even. Okay, so in this video though, our objectives are to express the area bounded by two curves as a definite integral, right? So instead of just one curve and the x-axis, we'll be able to do two curves. And then also we're going to deal with more difficult situations, like when graphs cross and things like this. So before we get to that though, let's kind of start with the basics here. Here's a nice theorem. Suppose we have two functions, f and g. They're nice and continuous on our interval from a to b. And suppose that f of x is always the bigger function, right? It's taller. It has a bigger y value everywhere between a and b. So let me go ahead and maybe graph this situation so far. So suppose we have this nice a and b. We have continuous functions, and our f of x function's the bigger one. So maybe it's up here. Something like this. Here is our f function, and our g function, it's a bit smaller, so something like this. So here is our g function. So on this interval, right, from a to b, f is always on top, g is on bottom. Okay, so if we have this scenario, then the area of the region in between the graphs f of x and g of x on this interval, well, we'll be able to write that down, but let's first maybe kind of shade this thing. So the area that we're trying to find is the area in between these things. So this area right here is what we're trying to find. And as you would probably guess, right, this is going to be the area under f minus the area under g. Right? So here's the area under g. So if I just figure out what is the area under f and then subtract away this purple area, this should give us the area between the functions. So this is going to be the area under f, so f of x, subtract away the area under g, so subtract away g of x, and then dx. There we go. So that's going to be our area formula in this case. So let's try it out. Find the area bounded between y equals 1 and y equals 5 minus x squared. So okay, looking at this graph here, I see the nice straight line is y equals 1. And this parabola looking thing, right, that's probably going to be our 5 minus x squared. Okay, so first of all, if I was to go ahead and calculate out the integral of just regular old 5 minus x squared, right, this would give us all the way to the very bottom, right, all the way until the x-axis. But now we kind of have, another function here. We have this 1. So we take the big function, in this case, right, the 5 minus x squared is on top. It's the bigger function. It's our f of x. And then we subtract away the smaller function. So I'm going to go ahead and subtract away this g of x. So that g of x in this case is just 1. So I'm subtracting away 1. And so now we need to figure out what should my bounds of integration be? Well, I should start and stop kind of where these things cross. So wherever these things cross, those should be my bounds of integration. So where do they cross? Well, that's kind of an algebra question, right? We set these things equal to each other. So 1 is equal to 5 minus x squared. So that gives us x squared is equal to 4. So therefore, x should be equal to either plus or minus 2 after taking the square root there. So if I want to find out this area, I'm going to be integrating from negative 2 to 2. So in this case, let's see, 5 minus 1 would be 4 minus x squared. And again, we're integrating from negative 2 to 2. So we find the antiderivative here. That's going to be 4x minus 1/3 x cubed. And again, we evaluate from negative 2 to 2. So if I plugged in 2, for instance, I would get 8 minus 8/3. And then I subtract away, if I was to plug in negative 2, I would have negative 8. And let's see, minus, and this would be negative 8/3, so negative 8/3, so minus a negative, that's going to be plus there. So let's see, I'm going to have, 8 is the same thing as, 8 firsts multiplied by 3 on top and bottom, that's going to be 24/3. So 24/3 minus 8/3, that's going to be 16/3. And then I subtract away, And here I have negative 24 thirds plus 8 thirds. So that's going to be negative 16 thirds. So let's see, 16 thirds minus a negative, so that's going to be plus another 16 thirds. That's going to be 32 thirds when all is said and done. So the area kind of bounded between these two functions is going to be 32 thirds. All right, so this was actually a relatively nice situation. The claim is that this theorem is pretty limited though, right? It only applies if we have one function's the big function the entire time, like f of x, and then one function's the small function all the time, like g of x. But there are more general cases, like when graphs cross and things like this. And in that case, we need to use kind of an upgrade theorem. So suppose we just have f of x and g of x. These are still nice continuous functions. They're talking about some region bounded by these graphs that's trapped in between these two graphs. But now we don't have the specification that one's always bigger than the other. In this case, the area can still be written down, but now this is going to be the integral from a to b, again these are our bounds, start at a, end at b, of f of x minus g of x. But when this value ends up being negative, we still want to count it as positive area, right? This is not net area, it is actual area. So area should never be negative. And therefore we sprinkle in these absolute value signs to kind of guarantee that this quantity right here is going to be positive. Again, kind of before we could guarantee it's going to be positive because we had a bigger value subtracting away a smaller value, right? Bigger value subtracting away a smaller value, so you always knew it was going to be positive, that we were adding up a bunch of positive numbers. But now in this case, if you're not making this restriction, right, one has to be bigger than the other, well, another way to make sure that it's positive is by using absolute values. So this is kind of the more general situation where maybe you can't specify which one's always on top versus which one's on bottom. So this is a nice theorem to write down, but I find kind of in these situations that we get ourselves into in these problems sort of deal, we usually just break it up into pieces. Let me show you what I mean by that. So we have this example here. Find the area between y equals x squared and y equals x minus 2/3 on the interval from 0 to 3. And then I went ahead and I gave us the Desmos Calculator to show us what this thing actually looks like. So you can punch this into your browser and kind of play with it, or I'll show you here. So I have it already loaded and stuff. So here's x squared and 3 minus 2x. Again, we're on the interval from 0 to 3. And you can see for a while, kind of this line, this 3 minus 2x is the big function. It's on top. It has bigger y values. And the smaller function is x squared. But then at 1, kind of we make this change, right? Something changes here. And now the bigger function is actually the parabola, x squared, and their smaller function is the line. Okay, so this is great. It gives us a nice visualization of what's going on here, but I want to pretend like what happens if this came up on a quiz or an exam or something where we don't have technology or calculators to be able to graph this out. How would we solve this problem? So let's get started. First of all, I know from our previous theorem that we want to evaluate out the integral from 0 to 3 of the absolute value of x squared minus 3 minus 2x dx. And as I have it written right here, I would probably get some points marked off, right? Because I need to subtract away all of 3 minus 2x. So make sure you include parentheses, or you can distribute that negative sign. But if you don't do one of those two things, right, you might get some points marked off, especially if you continue that error forward sort of deal. Okay, so here is my f of x minus my g of x. Again, I'm not sure which one's on top versus which one's on bottom. So, okay, we have this absolute value, and the claim is, right, evaluating out absolute values antiderivatives is complicated, just like evaluating out absolute value derivatives. And so we need to break this up versus, is this thing positive or is this thing negative? And that's kind of equivalent to, is x squared on top or is x squared on bottom? And so let's go ahead and draw out a number line, right, for absolute values here. So this is going to be from 0 to 3. That's the only time that I really care about. And let's take the thing that we're plugging into the absolute value. In this case, it's x squared minus 3. And actually, let me distribute that negative sign. So minus 3 plus 2x. And I want to know, when is this equal to 0? Because when it's equal to 0, right, this could make the transition between positives and negatives or negatives to positives. Right? I'm really trying to figure out, is, are we plugging in a positive number or a negative number into this absolute value? Because then the absolute value behaves very differently if you're plugging in a positive versus if you're plugging in a negative. So again, I'm going to first figure out when am I plugging in 0. So looking at this, maybe I'll go ahead and rearrange here. So x squared plus 2x minus 3 is equal to 0. And so I think this factors, right, into x plus 3 and x minus 1. Double check if I FOIL this all out. Do I get back to where I started? Yes. So this is saying that I would be plugging in 0 if either x was equal to negative 3 or if x was equal to 1. So in this case, right, I'm not going to be plugging in negative 3 because it's just not on my interval, but I certainly could be plugging in 1. So first of all, let's relate this back to our graph here, because we actually can use technology and see what we're doing. This is showing where do these two functions equal one another, right? Where do you have this cross? And so kind of via this graph, we would say, well, yeah, we should split it up from 0 to 1 and then from 1 to 3. But how do we find that algebraically? Well, that's where those two things are equal to one another, or when inside of this absolute value, right, you get out 0. So that's how you find that value, that special value 1. Now next up, we would plug in some test values. For instance, if I was to plug in maybe like a half, that's 0.5, or something like 2, right, into this original function here that we're inputting into the absolute values. Again, we're trying to figure out, am I inputting positive numbers or negative numbers? So I'm going to go ahead and start with 2 first. So if I plugged in 2, let's see, I would get 2 squared would be 4, minus 3, plus 2 times 2 would be another 4. So this is going to be equal to 5, which is certainly greater than 0. So on this interval, we're plugging in positives. Now on the other interval, I got to plug in, well, 0.5. Without a calculator, I like to actually, use this as a fraction. So I'm going to be plugging in a half. So 1/2. So if I square a half, I would get a fourth, minus 3, and then let's see, 1/2 times 2 would be plus 1. So this is going to be 1/4, let's see, minus 2, and that's certainly going to be negative. So on this interval right here, we're plugging in negatives. Okay, so again, this work right here really says that we should break up our integral. We should break it up on the interval from 0 to 1 of stuff, and then on the interval from 1 to 3. Again, this is really kind of using this pit stop theorem that we can break up our integrals, our definite integrals, and kind of take a break at 1, go get a coffee, right, and then come back and we'll continue integrating from 1 to 3. Now, on the interval from 1 to 3, the thing that we're plugging into the absolute value here is already positive. So the absolute values say, fine, I'm happy with this. Let's leave it alone. So we're going to get just regular old x squared minus 3 minus 2x. Now on the interval from 0 to 1 though, right, we're plugging in a negative value. So the absolute values are going to take that negative value and say, hold on, let me go ahead and throw in my own negative value, right, a second negative value, so that way the negative of a negative is positive. So this is going to give me negative x squared plus 3 minus 2x. And so let me go ahead and rewrite this one more time here. So I'm going to go ahead and switch the order, right? So this is going to be 3 minus 2x minus x squared dx plus the integral from 1 to 3 of x squared minus 3 minus 2x dx. And then I'll go ahead and start evaluating, but I want to show you kind of on the graph what we've done here. Again, this is kind of all the algebraic stuff, but all this has identified that on this first interval, right, from 0 to 1, this is saying that the line is bigger than the parabola, right? Because this comes first. The line is bigger than the parabola. So if I again go back here, I'll see that yes, my line is bigger than my parabola. It's on top. And then on my second interval, right, from 1 to 3, we see that the parabola is bigger than the line, right? It's on top. So again, the parabola, this red line here, is bigger. The parabola is bigger than the blue line here. So that's how the absolute values are actually working out. And this is how, if we didn't have a picture, we could still solve this. All right, now at this point, it's just kind of solving it out. I recommend pausing the video, getting as far as you can, and then I'll go ahead and spoil the surprise. All right, so this is what I got. So evaluating, right, taking out this evaluating the indefinite integral here, or taking the antiderivative, I get this. Evaluating from 0 to 1. Similarly here, taking the antiderivative, and then I need to evaluate from 1 to 3. So now I go ahead and I plug in these values. Of course, when I plug in 0, I just get out 0. Plugging in 1, I get this value here. And for my second one, let's see, plugging in 3, I get 9 minus 9 plus 9. And then subtracting away, when I plug in 1, there we are. And we can see that kind of this first evaluation right here, I get 5/3. And for my second one, on the interval from 1 to 3, I get 32/3. And we can see that both of these are positive numbers, right? They're referring to some area. And we can actually see that this purple one here, the second one from 1 to 3, is a lot bigger of a number than my first one. And this actually refers to the graph. I now shaded the second one purple, right? On the interval from 0 to 1, the claim is this area right here is this 5/3 value. And then on the interval from 1 to 3, again, you can see that this is a lot bigger. This is going to be this 32/3. So that's that purple area there. So those are the values that we figured out. Again, they're both positive. If that one of them was negative, that would be relatively concerning because, again, this is area, not net area. Okay, so overall my answer is 37/3. When I add these together, again, that's the area between x squared and 3 minus 2x on the interval from 0 to 3. All right, and so I have one more example for us. And there's another thing that sometimes comes up is that sometimes these functions can actually switch on us. So not only kind of which one's on bottom versus which one's on top, but maybe a completely change, between functions. So in this case, I have 3 functions here. Y equals x, y equals 4 minus x, and y equals 4 minus x over 3. And again, I would like to figure out the area bounded between these things. All right, so I'm going to set up a definite integral, or integrals, that represent the area bounded between them. Notice it doesn't say to actually evaluate this out, but we're just going to do the setup. I think that's the difficult part here. So okay, let's actually sketch these out and see what the situation looks like. So maybe first of all, I'm going to sketch y equals x. So y equals x, again, we're going to have maybe 1, 1, we're going to have 2, 2. I'm just plotting some numbers here. Again, this is going to be a nice straight line. So a nice straight line here. Slope is 1, the intercept 0. So there we go. That is my y equals x right here. Next up, maybe in green or so, I'm going to sketch the function 4 minus x. So y equals 4 minus x. So when I plug in 0 for x, I get out 4 for y. When I plug in 1 for x, I get out 3 for y. When I plug in 2 for x, I get 2 for y, so on and so forth. So this is a nice straight line. The intercept's at 4, and the slope is -1. So there we go. So this is my line y equals 4 minus x. And then finally, maybe in purple or so, I'm going to sketch y equals 4 minus x over 3. So first of all, maybe if I was to plug in x equals 0, I would get out the value 4. But then there's some fractions here. So actually the next nice value to plug in, right, so I did x equals 0 implies y equals 4. But if I did x equals 3 maybe, so x equals 3, right, because we'd have 3 divided by 3, so that would be 1. So 4 minus 1 would be 3. So we get y equals 3. So when I plug in 3, I get out 3. So when I plug in 3, I get out 3. So that's something like this. And so now, again, this is a straight line. So I'm just going to connect these with the straightest line that I can here on my tablet. So something like this. And so this purple line, again, is y equals 4 minus x over 3. And so I want to figure out the area bounded between these things. Right? So there's lots of kind of regions here, but the only one that's kind of bounded between all 3 of them, that's stuck between all 3 of them, is this triangle-y thing right here. Okay, so let's go back to kind of our original theorem here, and I'm going to write this in red because it's an idea that gets us headed in the right direction, but it's not quite right. So I'm going to cross this out here in a little bit. Right, we can see that kind of we're integrating between 0 and 3. Kind of that's where our region exists. So I'm going to be integrating from 0 to 3. And we're going to do our big function, so our f of x, our big function minus our small function. Right? So let's see here. From 0 to 3, our big function, our value, or one that has the biggest y values, that's on the top, right, is this 4 minus x over 3. So I'm going to do 4 minus x over 3. So that's our big function, and now we subtract away our small function. And here's where we run into an issue, right? Because our small function on this piece right here, kind of as x travels from 0 to 2, right, our small function is this green one. It's this 4 minus x. So I'd like to say subtract away 4 minus x. But that's not quite right, right? Because later on, right, this would be too small. Kind of, it's actually bounded by this blue function on the interval from 2 to 3. So from 2 to 3, it's bounded on the bottom by y equals x. And so again, this isn't quite right. We have to break up this integral. So I'm going to go ahead and cross this out. And this comes up with the idea that let's go ahead, in order to get this area, let's break it up and do the interval from 0 to 2 of some big function minus some small function, dx. And then again on the interval, right, from 2 to 3 of some big function minus some small function, dx. Because again, at 2 here, kind of we see that the small functions, they change on us, right? And that's what I said, right? The functions can switch on us. In this case, the small function, it switches from 4 minus x to y equals x. Okay, so on the interval from 0 to 2, the big function is 4 minus x over 3. And the small function is this green one. It's the 4 minus x. Then on the interval from 2 to 3, the big function is still 4 minus x over 3, but the small function has changed. And actually on this interval, the small function, right, the thing that's bounded below, is by this y equals x. So I'm going to subtract away x. All right, so this would be my final answer. Again, we were just asked to set it up, and I think that's really the hard part, is setting this up. There we go. And just in case, I mean, if you want to evaluate this all out, I did kind of on the side here. And this one right here is 4/3. And the second integral is 2/3. So that is, right, this 4/3 area is this one right here. So that's our 4/3. And then our 2/3 area, maybe I'll use green or so. This 2/3 area is this one right here. So which kind of makes sense, right? The 4/3, it does look bigger than the 2/3. Of course, when you add these all together, you get 6/3, or that's the same thing as 2. So the overall area of this triangle, this thing that's trapped between these curves, is just area 2. But again, our quest was really to set up the definite integral, or integrals, right, as we're given right here, not to evaluate them out. All right, that's it for our first video. We got one more, right? I kind of alluded to this fact that sometimes it'll be advantageous to actually integrate with respect to y instead of with respect to x. So that's going to be topic for our second and last video for this section. I'll see you then.